Okay, so last class we have this, we saw this remarkable result that every NFA can also be simulated by a DFA, which was kind of coming full circle, right? We started out by saying, okay, there's some things which you are not able to do with the DFA, but then we introduced NFA, and now we are back fully to saying that every NFA is also a DFA. But this layer of abstraction makes everything cleaner, modular, and much more useful for many other applications. And this is something that you see throughout computer science, where you introduce an abstraction with the goal of making things cleaner, but then it also has practical applications. Okay. So let's do another example of this conversion to just get a sense of what non-determinism is and how it helps us. And then we'll segue into another great classical topic called regular expressions. So that's our agenda for today. Okay. So we saw something like this in last class too, but I want to work through a related example today. Okay, so let's consider the language L, which are all X, such that the second position from the end is a 1. Okay. So the second bit from the end is a 1. Right, so we saw an NFA for this language. We saw a related NFA where the third bit from the end is a 1. Let's do it for the second bit, because if I do it for the third bit, then it's going to be very messy to convert it into a DFA. Okay. So what's an NFA for this? So I can draw a simple NFA for this. This is my start state. And any suggestions on what the NFA should be if I want to recognize all strings whose second bit from the end is a 1. And as a hint, I want to say that you can do it with only 3 states. Any ideas? You can either type or just unmute yourself and shout it out. So, if we see a 0, we stay where we are. Okay. And the power of the NFA is we can guess when we are going to start looking for the end of the string. So here's a simple way to do that. When I see a 1, I'm going to assume at some point that I'm looking for the end of the string. Okay. So this is a NFA for L. Does it make sense? So whenever there is one branch which assumes that, okay, this is the last but one position, and then starts going there. So this is NFA. Let's call it N. And now let's convert it to a DFA D. Okay. So how can I do that? We pretty much know exactly what we need to do. So there are 3 states. So when we convert it to a DFA, we're going to end up with 2 to the 3, so which is 8 states. Okay. So we have states. Let me draw these a little bigger. Okay, so we will have a state for every possible subset of the original collection of states of the NFA, right? So here, for instance, I have a state like this. So I'm just enumerating all possible subsets, and this is one way to do it. And these are my states. Okay. And I'll draw a few edges and then I'll complete the diagram. Okay. So let's find out, okay, what should the start state be? If I follow the conversion that we talked about in the last lecture of converting any NFA to a DFA, what should the start state be in this new DFA that we're going to construct? 0, perfect. Right, so this should be the start state. Okay, so the start state should be all those things which are reachable by only epsilon edges from the original start state, but we don't have any epsilon edges, so it's just going to be this set. Okay, and so what is T of 0, 0? Well, you're just going to get a self loop. And how about T of 0, 1? This should be the set of edges, the set of states that you can reach by one edge from in N from the state 0. So if I follow one edge, I can either reach 0 or I can reach 1, right? So I'm going to get this. Any questions? Okay. I'm sure you can follow this, right? So this is going to be 0, 1. Let's do a couple more. So what is T of 1, 0? Well, if I'm in the state 1 and I see 0, there's only one state I can reach, which is 2. Oops. Okay, and how about T of 1, 1? Again, it's just the state 2. Okay, and you can now finish, fill up all the remaining edges. I'm not gonna do that here, but you can. Okay, let's do one more. So what is T of 2, 0? If I'm in this state, the state corresponding to the set 2, and I read 0, where do I end up at? Well, if you go to 2 here, there is no outgoing edge. So what does that mean? What should you transition to? The null set, right? Because that's kind of the dead state here. Okay, so this is going to be 0, 1. All right. And let's do one last one, which is, so it's going to be the null set. T of 2, 1 is also the null set. And how about T of 1, 2 and 0? So if I'm here and I see the edge 0, where should I go to? Any guesses? Well, under the definition, I should go to T of 1, 0 union, let's say this is TD. Okay. And what is T of 1, 0? You just end up in the state 2, whereas this is the empty set, right? So, I mean, as can happen here, when I take the transition, I end up just in the state 2. Okay, so here I'm losing one element, there's nothing precluding that can happen, and that's exactly what's happening. Okay, and you can fill through all of the remaining stuff just by drawing the arrows. Let me sort of jump ahead. Okay, so you can complete the diagram, and this is going to be your DFA for recognizing if the last bit from the end is a 1. Okay, you can play this game always, right? So let's say, for whatever crazy reason, I'm having a bad day, so I'm going to torture you by asking you to do the following. L is, I'm not having a bad day, I'm just kidding, but let's say L is the set of all strings such that the 10th bit from the end is 1. Okay. If you tell me this, I can easily draw an NFA for it. So what's the NFA? I can follow the exact same logic as before, right? Right, so I can use the exact same logic as before, as we did for the second bit from the end being 1. I just have 10 states, 0, 1. This is a 1, 0, 1. Yes, we need one more. And this is my accept state. Oh, actually, we forgot to do one thing here, which is what should the accept states in the previous diagram be? So under conversion, the acceptance states should be all those sets which contain the element 2. So the accept states should be all these guys. Okay. And why is there no outgoing edge for 1 bit from 0, 10? Oh, there should be. Did I not draw that? Okay, so thanks for catching that. There should be, and I think it just goes here. Yeah, thank you. Yeah. So the 1 edge kind of goes back to 0. Yeah, I might have not drawn all the edges, but you should always kind of follow through with this. Okay. So here's a 11 state NFA, which can check if the 10th bit from the end is a 1. Okay. Now, if I ask you to convert it to a DFA, then that would be awful, right? Why awful? You need 2 to the 11, which is 48 states. Okay. As good as scribble together is, I don't think I'm gonna draw it here. But you might ask, this is one way to convert an NFA into a DFA, right? But maybe for this language, where I'm looking for just the 10th bit from the end being 1, that seems simple enough, right? Maybe there is a different DFA that I can draw, which has very few states. What do you think? How many states would you need to, straight out draw a DFA for this language? Any guesses? Well, as it turns out, there is no silver lining here. This is a statement that we're not going to show, but you can ask me about it in office hours or for me to explain why that is true. But okay. So there is an NFA with only 11 states. And in fact, the non-determinism is somehow very minor, right? Because there's only one edge where one node and one edge where we're kind of violating the non-determinism. The state, the start state has 2 edges labeled 1. That's it, right? But the smallest DFA for this language requires 1024 states, right? So when we did this conversion, we were losing an exponential, we were incurring an exponential blow up in the number of states from converting an NFA to a DFA. And this claim is essentially saying this is unavoidable. Okay, and it's unavoidable even for like a seemingly very simple language and a simple NFA. Yeah, definitely. So that's a very good point. For it only applies to this specific okay. It only applies to this specific L where I'm looking for the 10th bit. If I am looking for, 17th bit, then it's going to be 2 to the 17th, basically. That's the conversion. You can show that if I want to check for the last bit from the end, the kth bit from the end, you need 2 to the k states with a DFA. Okay. So even though, in some sense, in terms of total computational power, we could have cut out the middleman NFA and said every DFA is an NFA, every NFA is a DFA in the end. It's really helpful as an abstraction to think about and even to build things because NFAs are much more compact. Okay. Any other questions about this distinction? Okay, so that's the main thing I wanted to say about NFAs and DFAs, but let me summarize a little bit of what we were doing, right? So we defined DFAs, we defined NFAs, and we also studied their closure properties, right? It's kind of just a silly table I'm going to draw. Okay, so let me draw a silly table. We know that DFAs are closed under AND. Yes. And we saw this, let me say directly. By directly, I just mean that, we constructed a DFA with, by multiplying the number of states to get a DFA for the AND of two DFAs, okay? So all of this we could do directly. Now, how about concatenation? Are DFAs closed under concatenation? If I tell you that here are two languages, I have a DFA for L1, I have a DFA for L2. Do I get a DFA for the concatenation now? Yes or no? Well, yes, right? Because we saw already that there is an NFA for the concatenation, but then I can go back. So DFAs closed under so we can state as a theorem that DFAs are closed under concatenation. Okay, why is that? Well, if L1 has a DFA, L2 has a DFA, then we can build a NFA for their concatenation. Okay, we saw this maybe 2 lectures ago, right? That was one of the way we motivated defining NFA. We could easily build an NFA for the concatenation of 2 DFAs. Okay, but then by our theorem can build a DFA for the NFA. Okay, so this is one way to show that DFAs are closed under concatenation. Basically, we said, okay, you concatenate 2 things. I first build an NFA, and then I'll convert the NFA into a DFA. Okay, it's kind of a little bit roundabout, but that's pretty much the simplest way we know of showing that the concatenation of 2 DFAs is still recognizable by a DFA. Okay. Oh, sorry. Let me say. Closed. So by closed, I just mean that, if I take the AND of 2 DFAs, then that is also recognizable by a DFA. Okay. Does it make sense? And the same for NOT. Like, if I take the NOT of a function computed by a DFA, then that is also computable by a DFA. That's what this is trying to show, right? So closure properties. Does it make sense? Right. So a while back we saw that if I have 2 languages and they're AND 2 DFAs, then the AND is also computable by DFA and so on. Okay. So by this conversion, by putting these 2 things together, that you could build an NFA for the concatenation and then convert an NFA to a DFA, we immediately get these, that DFAs are closed under concatenation, and the same for the clean star operation. Okay, so if I gave you 2 DFAs and asked you, if I gave you a DFA and asked you to build a DFA for the clean star, pretty much the only way we know is first build an NFA for the clean star and then convert that back into a DFA. Okay. All right. And just for the same reason, we would get that all of these NFA properties, the NFAs are also closed under all these operations, because essentially all we just showed is that NFAs are also equivalent to DFAs. Okay, so let me the corollary say okay. And why is that? The proof is, again, let's say you have if L1 has an NFA, L2 has an NFA, then first build equivalent DFAs and use DFA closure properties. Okay, since they are equivalent models, you would get that all these NFAs are also closed. Okay, but let me ask you one sort of puzzle, right? And the puzzle is about not of an NFA. Suppose, I have a function Suppose I have a function which is computed by a NFA. How can I get an NFA for the negation of F, right? If it was a DFA, what could we do, or what did we do, many lectures ago? If I ask you to negate the function computed by a DFA, what did we say we could do? So just to recall, to negate a DFA, we could, exactly, right? We could flip the accept/reject states, right? So, if F is computed by DFA D, which is P comma S, then not of F is computed by DFA, which was P, and all things not in S. Okay. So I'm just saying, suppose I actually gave you an NFA N. I don't have to specify, just some NFA. Then I'm asking you, how can I get an NFA? Can I get an NFA for that computes not of the function? Okay. Just to kind of compare with where we were earlier, we did something similar for a DFA, right? As pointed out here, we could just flip the accept and reject states and change how, get the negation, right? Can I do something like this for an NFA? What do you think? What happens if I just flip the set of things? If there is a DFA for L, then there is an NFA for it. So yes, I guess we would have to do it the other way, right? So we would first build a DFA for F by converting the NFA to DFA, and then flip the accept and reject states. Okay. There's no difference. It's the same thing. Do I agree? But just as a warning, if I just try to change the accept and reject states for an NFA, then you don't flip the language. Okay. So this same construction, same idea, won't directly work on an NFA.
Oh, sorry, can I have a question?
Yeah.
Yeah, so after you did the split for this DFA generated, how did you convert it back to an NFA? Because now like this accepted state might not like.
So any DFA is also a NFA, right? It's just a special kind of, so we don't have to convert it back. You know, you just found something which is NFA is just a strict generalization, right? Or at least definition wise. Okay. But this is just a warning that there is this, you know, when working with NFAs, we have to be careful. If I just flip the accept and reject states in an NFA, that does something very weird. Like, you know, it's not just going to flip the output of the function, right? And that is because for a state to be accepted in an NFA, you only need one of the multiple paths to end up in an accepting state, right? But the other ones need not be in accepting states. So when I flip, you might not be doing anything meaningful. Okay. Any questions about this? This is just a warning that, you know, there is still subtlety in these definitions and the power of this implication for NFAs to DFAs. Okay. All right. So those are the main things I wanted to say about NFAs and DFAs. And now I want to talk about, yeah, so basically it won't work directly. If I just do this flip, then it's not going to work. So you have to first convert it to a DFA and then do the flip, and then it will work. Okay. And I encourage you to come up with an example to explicitly see this, and it's worth doing it to just see it in action. Okay. All right. So now that we know what NFAs and DFAs are, they both have their own purposes, right? You know, certain kind of closure operations are easier to see when you look at them from a DFA perspective. Certain things are easier when you look at them from an NFA perspective. Like NOT is very easy if you're doing DFAs. Concatenation is easy if you're doing NFAs, but then we can go from one to the other. So, you know, you can always take the easiest path forward. Okay. And in the remainder of this lecture today, I want to talk about one other way to talk about similar things as I've been doing so far. but it's from a different perspective, and it also has some very important practical applications. And this is the world of regular expressions. Okay. So, I mean, if you've done any programming, like, you might have seen regular expressions before. Yeah, it's exactly regex. If you use Unix, they're everywhere. They're one of the most fundamental tools in any programmer's toolkit. And also in many applications, like they're really critical in database systems, in filtering out all kinds of crazy forms and everything. People use regular expressions left and right. But you might have not realized this, but at the core of even the most practical systems on regular expressions are DFAs and NFAs. Okay. So let's dive into that a little and see how the theoretical stuff that we are doing is actually playing a major role behind the scenes. Okay, so there are many ways to motivate regular expressions, but let me take this perspective of viewing regular expressions as some way of pattern matching. Okay. So pattern matching problems are, one of the most, like, they've been studied for almost 50 years, and they occur in many, many different forms. So for instance, you might be looking for a specific, set of lyrics, right? I want to find this sequence of text in, some book. I want to find, maybe my email address in some email database. That's a little bit of pattern matching, right? So let's start with the simplest pattern matching problem. Okay, so pattern matching problem. The simplest thing is you have some text. Okay, and we'll think of the text again. Really imagine you have a huge Wikipedia database or something, right? And I want to find if there is the specific string sequence, let's say pattern matching problem. That's my string sequence occurs anywhere in my text. Okay, so that's my goal. So for instance, the camera did something weird. It's a fancy camera. It's supposed to recognize hand gestures. I guess it does randomly. Never mind. Okay, so let's think of the text as I have some long sequence X. And I'm specializing to binary strings just because it's simpler, and you don't, when you actually implement these things, usually it's over the English alphabet or something like that, right? And then there's a pattern, which is another string sequence. You should think of it as, maybe this is X, the text is very long. Maybe it's all of Shakespeare's plays put together in one file. And the pattern is one particular verse that you're trying to find. Okay. And the question, does P occur in X? And then you might also wonder, if yes, can you find where it is? Okay. That is, does the pattern P, somehow I want to say that the string X contains the pattern P somewhere within it. This is like a typical pattern matching problem. And you should think of, maybe X is a huge string, maybe 1 million bits, and P is just 1001010. Okay. If I don't tell you anything about anything else, what's the algorithm that you would use for this problem? Okay, what algorithm would you use for this problem? If I just ask you to go ahead and solve this in, let's say Python, what would you do? Well, what you do is, let's say I'll define so how can I solve this problem? I can do, the straightforward single for loop, check everything, exactly, right? Linear scan, it's like the sliding window scan, right? So you'll say def pattern match X comma P, let's say L equals length let's not worry about the border cases. Check if, starting from, okay, so I'm just single for loop to keep checking. Okay, that's it, right? That's a very nice simple algorithm, but let's think about this for a second, right? If I tell you my pattern is maybe, let's say m bits long, right? And my string X is n bits long. How many operations does this simple algorithm perform? N times m, right? Oh no, it's not n minus m, right? Because you're running the loop n minus m times, but checking this always takes m steps, right? Imagine m is like 100 bits and my string is 1 million bits. So if I'm looking for a pattern of length 100 in a 1 million bit long string, I'm going to perform 100 million operations, right? Because every time I slide a window, I need to check if I match exactly for these 100 things, right? Yeah. So you have to think of this entire block, right? You have this equality sign is really shorthand. I do have to, the only way I can check equality is to match these entries one by one, right? Okay. I mean, you can think you can do some dictionary data structure or whatever, but like even that is going to incur the same kind of cost. Okay. So this is good, but still, like, imagine if I had 1 million bits and my P is 100 bits, that's 100 million operations. 1 million bits might seem too excessive, but that's how many bytes really? It's 1 megabyte or something. It's a tiny document, right? There are documents which are like 100 megabytes, let's say, and I want to look for a text in that document. How am I going to do that without doing this n times n time, which is really bad? Okay. So we are not going to do that here in this class, but let me just hint at the power of abstraction, right? So there is this famous algorithm called Knuth, Morris, Pratt, or KMP string matching algorithm. Okay. There are various ways to define it, but the best way to picture it is what it does is it has two steps. Given P, find a DFA D on P plus 1 states. Okay. So it defines a DFA on P plus 1 states, and then output 1 if D accepts X. Right. Somehow checking whether the pattern occurs anywhere in the string can be reduced to checking whether a particular DFA accepts the string X. Okay. You've done few toy examples of this, right? You looked at examples where trying to check if the string 101 occurred in the string, this pattern 101 occurred in the string, or 010 occurred in the string. But there's something much more general, which is true, and which is actually useful in practice. There are variants of this which people use, but I think this is a remarkable algorithm. Really a beautiful algorithm. And the game here is that the entire thing only performs so it only performs n plus m operations instead of m times n. Okay. Sorry, this should be m plus 1 states. Okay. And the reason is that basically it's going to build a DFA with m plus 1 states, and each time you read a bit of X and then kind of take a step in the transition, take a step in the transition diagram of the DFA, and keep on going like this, right? And is like single pass. Okay. So again, this is kind of, it takes a lot of work, a lot of ingenuity in defining this DFA, right? But at the heart of this pattern matching is this notion that I can capture this pattern by a DFA, and then I'll run an X through the DFA and output 1 if it accepts. Yeah, exactly, right? So essentially, you don't even have to represent our DFA as a graph. You think of your DFA as being given by a table, right? By a 2D table. So if you're doing it in Python, that's an excellent question. Doing it in Python. So what you do is, first step, is process P to a DFA D. Okay, and what does this DFA do? You can think of it as a two-dimensional array. Okay, and what's the two-dimensional array? The first one tells you the state, and then the next one is a bit and tells you what's the output after taking the transition, right? So the transition diagram is just a 2D array. Right, so this is 0, 1 up to P, bit 0, bit 1. What are the transitions? Okay, and then you simulate D on X. And this you can do easily by a simple for loop. And now each step of the for loop only takes one operation, one lookup in this table, and that's it. Okay, does it answer your question, Eugene? So it's a really beautiful algorithm, but the crux of the matter is capturing the pattern by DFA. Okay. So where do regular expressions come in, right? You know, this is, what's the last character? Oh, that should be M, sorry. The size of the table is basically there are m+1 states in the DFA and the alphabet is 2. So you're exactly going to get that. It's basically an adjacency list, yes. But the graph is simple in that, you know, it's kind of like going, it's a simpler graph. So instead of thinking of it as a graph, if you just think of it as two lists, it's easier for simulation. Okay. So now, when we think of regular expressions, they are really generalizations of this pattern matching problem. Okay. So, for instance, so what's the motivation for this? Right. So the motivation is that often, you know, maybe I don't want to look for the exact pattern P appearing in the string X, but maybe there is some flexibility in matching the pattern. Right. So for instance, there is a disease, and then there's something called the Fragile X syndrome. Okay. And what is Fragile X syndrome? It's basically a disease which is a genetic disease, which you can identify by just looking at the genomic sequence of an individual, right? But a genomic sequence is huge, it's humongous. So you have your DNA sequence. Okay, and this is the DNA sequence of a person. And you can say that the person, basically the sequence has this syndrome. So the DNA sequence is a string of elements from A, C, G, T star. You just have a sequence of A, C, G, Ts, right? And what you're looking for in this sequence is if it contains the following pattern. So you're looking for some string which has GCG, ends with CTG, and then you must have repeats of CGG or AGG. Okay, so often when you're looking for this sort of, you know, flags in genomic sequences, you're not looking for exact pattern matches, right? There could be variants, but you're still fine with it. So for instance, whenever, if your genome contains a sequence GCG, CGG, CTG, or something like okay. If your sequence contains any of these patterns, then you have the syndrome. Okay. So the question we could ask is, how can I identify whether my genomic sequence contains any of these patterns? Like, there's a text description, which is GCGs with some repeats of either CGG or AGG, one of these two things, and then CTG. Okay. And you can come up with all kinds of scenarios where this is useful, right? Later on, I'll talk about one of the most important tools in operating systems, which is grep, which again comes back to this sort of pattern matching. Okay. But before we start talking about these problems, we should ask two questions, right? How can I specify this my goal, my target, in a way that machines can understand, right? I can't say, okay, GCG and then repeats of CGG or AGG and CTG. If I tell you this, how can I look for this, right? It's a very English description. We need a more formal way to talk about these things. And then we can ask, how can I even find whether my sequence contains or matches such a pattern? Okay, and the way to do this comes from the language of regular expressions. Just as you have arithmetic formulas for building up, big numbers from small numbers, regular expressions are a way to build massive sets of strings, kind of a succinct way to represent collections of strings, not just a single pattern, but maybe multiple sequences in one short way. Okay, so let's take a 5-minute break. And when we come back, we'll dig into pattern matching with regular expressions, what they are. I'll say a little bit about where they're useful, and then we'll connect it back to DFAs and NFAs. Okay? All right, so let's take a 5-minute break. All right, let's resume. So when you think of regular expressions, you might have seen, it's really an important part of programming toolkit. It has zillions of applications, processing natural languages, virus scanning. You can do anytime you use search and replace in editor, that is doing some form of regular expression matching, right? grep in Unix, right? And searching in genomic sequences. Even in program compilation, these things are useful. Okay, there are many applications of what regular expressions are. Okay, but as I said, at its core, they're a way to succinctly represent complicated sets of strings. Okay, and the way you define them is inductive. So how do you define them? You define them starting from what some basic objects are and then building on top of that. I'm only going to define regular expressions over the alphabet 0, 1. But again, just as it was true for non-deterministic finite automata, for deterministic finite automata, you can also talk about not just strings over 0, 1, over any alphabet, maybe over ACGE, and nothing would change. You would just replace 0, 1 with the alphabet and everything would go through. So there are some okay, so let me define this. So the way you define regular expressions is by starting with the base cases. Okay, so 0 is a regular expression. Okay, and 1 is a regular expression, is a valid regular expression. 0 is a valid regular expression, 1 is a valid regular expression. Okay, and so is the empty set. Phi is a valid regular expression. You'll see what this means. Okay, what does it mean to say valid? I'm just defining what are some allowed expressions, and then we'll interpret them. How do you use them? What do they mean? And things like that. Okay, and then there are compound cases. So what are compound cases? If R1, R2 are regular expressions, then R1, R2 is a regular expression. I'm going to abbreviate regular expression as RegEx. Okay. So the way to interpret this is R1 followed by R2. Okay. And R1 star is a RegEx. Okay, this is the analog of clean star operation that we saw. And lastly, you'll also see this notation R1 slash R2. So you should interpret this as R1 or R2. Okay. So, I mean, when I'm talking about it this way, it seems I'm doing something very circular and silly, right? And I'm defining regular expressions in terms of regular expressions. So is it a circular definition? Not really, because when I'm doing this, I'm decreasing the length. So I'm kind of building bigger, more complicated regular expressions from simpler regular expressions. So it is not circular and hence a valid way to define regular expressions. Okay. So phi is regular and then null string is also regular. And I should also say epsilon is a regular expression. Okay. Any questions about this? Let's do some examples. So 0 is a regular expression. Let me change. 0 is a valid regular expression. 1 is a valid regular expression. 0, 1, 0, 1, 0. Maybe 0, 1, 0 star. 1, 0, 1 star. Maybe 0, 1, 0, 1, 0, 1 whole star. And maybe 0 slash 1 star, and so on and so forth. Okay, so all of these things would be valid regular expressions. I can also have 0 slash 1 star, 0, 1, 0 slash 1 star, 0, 1, and maybe 0, 1, 0, 1, 0, 1 star. Okay, all of these will be valid regular expressions. I can also have nested star operations. That's also fine. Okay. But what's the point of defining these regular expressions, right? The point is that once you define what they are, you can also define an important operation you can perform with regular expressions. and which is matching. Okay, so this is an important definition. So we're going to look at matching regular expressions. Okay. So suppose I gave you a, we are given a string X and a regular expression R. So is this basically saying that any sequence of zeros or ones are regexes? Yes. In fact, it's more complicated, right? If I have any sequence of zeros and ones, I can also throw in this, slashes, which are going to be interpreted as OR operations or clean stars, which are like, stars. And then any of these sequences is a valid regex. Okay. This is the most basic form. And then when you go to modern programming languages, you have the same thing over more advanced alphabet. And you'll also have some shortcuts in modern alphabets, where instead of saying, okay, A, B, C, D through, all the alphabet, you just say A-Z. That corresponds to, the set A, B, C, D, E, F, G, and so on. Okay, but this is basically it. Regular expressions are just these sequences of operations. You just have to combine basic ones using, these are the basic ones, and then you can combine them using these rules, compound cases. Okay. So now, given a string X and a regex R, we're going to say that X matches R under some cases. Okay. So base cases. 0 matches 0. Okay. 1 matches 1. Again, kind of epsilon matches epsilon. All right. So far, so good. But now come the compound cases, which is where the real action is. Okay. So we say X matches a regular expression R1, R2 if I can break up X as a concatenation of two things. Okay. Where X1 matches R1 and X2 matches R2, right? So I have a regular expression like, 0, 1, right? So if it's 0, 1, then we say that X matches 0, 1 if I can break it up into two pieces where the first portion matches the first regular expression and the second portion of the input string X, it matches R2. So when you say matches, is it just an equality? Not necessarily. So we're getting more complicated in a little bit. So far, it almost seems like we're just checking for equality. But now the next compound cases can change that. So we say X matches R1 slash R2 if X matches R1, or X matches R2. Okay. So now it is no longer an equality. So we are really defining what matching means, right? So here X matches R1, R2 if it matches either R1 or R2. So it doesn't have to, for instance, equal either one. It could be, doesn't have to equal both, it is OR. Next, X matches R star if I can break up X into sequences as a concatenation of multiple pieces where each xi matches R. Okay. Note epsilon matches R star. Now there's some convention issue, but we'll basically say that the empty string matches R star for any pattern R. So this is a little bit like clean star. It's basically saying given any pattern R, any string X matches R star if I can break up X into pieces where each one matches R. Okay, does this make sense? This is a more complicated definition of matching, right? It's not just looking for whether a piece of X is equal to R, but it's really looking for this more complicated notion. Yes, is epsilon is the empty string really, like the null string. Okay, so let's look at some examples. This is a mouthful, but the definition is clear when you look at some examples. Okay, so do you think the string 0 matches 0 or 1? Yes. How about X equal to 1? Yes. How about X equals 0, 1? No, right? Because for it to match 0 or 1, it should equal, it should match either the pattern just 0 or the pattern 1, but neither of it matches. Okay, and so let's take more complicated examples. What matches 0/1 star? What strings would match the pattern, match the regex 0/1 star? Many things would match. What are all the strings that would match 0/1 star? Anything, right? Literally anything. So this is basically all strings, right? So 0/1 star is a very succinct way, just as we were doing before, of representing all strings. So you can think of one motivation for regex is a way to compress, to find a compact way of representing patterns. Okay. So for instance, next question. It's really a lot of fun to play with regular expressions and see, isn't 0/1 star saying the same thing? Exactly, it's saying the same thing. But how about what strings would match this regular expression 0/1 star 0? Anything that ends with 0. Okay, so instead of saying, okay, filter out all strings that end with 0, I can say find all strings which match the pattern 0/1 star 0. Okay, and so basically the reason is that take any string which ends with the 0 at the end. The way I would match it is I would match the 0 here to this guy and this to whatever prefix you might have. Okay, and you can ask the same thing again. What matches? Let's take some more complicated examples, right? What matches 10 star? What strings would match 10 star? Repetitions of 10, that's it. Okay. What matches 1 0 star 1? Well, an alternating string that starts and ends with 1. Okay, this is just a different way of saying the same thing, right? A rep of 1 0 that ends with 1, and it's exactly the same as saying an alternating string that starts and ends with 1. Okay, so you can combine things like this, right? You know, you can an alternating string that starts with 0, ends with 1. Okay, and you can build something like, you know, 0/1 0 star and 1 0 star / 1 1 0 star 0 1 star. So what matches this guy? So now I'm up the ante, right? I gave you a very complicated looking pattern, and I'm asking you what strings would match that pattern. What do you think? Well, you can kind of enumerate the cases, and you'll end up with saying that exactly any string with alternating symbols. Okay, and you know, the way, this is the reason that regular expressions come up is because, you know, you can find succinct ways to represent these kinds of things. So let's do one more example. I think this is a trickier one. Hold on. Okay, so what matches so what would match this string? What would match this regex? What strings would match this regex? Right, any string with exactly 3 1s. Right, so as long as the string has exactly 3 1s, it's going to match this string. Do the stars only apply to 0? Oh, only to 0. If it were to apply to 0, 1, then I have to put a parenthesis. That's a good question. Thanks. Okay. What matches? What would match this pattern? I just put a star on top of this. Exactly, any string with number of ones is a multiple of 3. Okay, as long as the number of ones is divisible by 3, it would match this pattern, and no other string would match this pattern. Okay, make sense? All right, one last one. What matches what strings would match this pattern? As a hint, we saw this already today. Any string, exactly, again, any string with 1 in the 3rd position from end. Okay, so you can see that you can hopefully you're getting a sense of these kinds of patterns, right? And like for instance, if I ask you to look for a valid email address, I input a text, and then sometimes when you're filling out these forms, it will say, okay, this is not a valid email address, right? The way the form is actually doing this is that there's a regular expression which kind of captures what's a valid email address, and then you're matching that, okay? So in general, when you generalize the alphabet, you get much more useful things. Okay, so now we have this notion of regular expressions, but for us, you can also view of them really as a program for doing some computation or defining a function. Okay. So what do I mean? If I give you a regular expression R, then I can define a corresponding language, which is all strings X, which match the pattern R, match the regex R. Okay, so we'll say that L is AKA L is recognized / computed by R. Okay, and we can also define a corresponding function which takes any string and just checks whether you match it or not. Okay. And once again, you can say that F is recognized / computed by R. All right. So why are we talking about these regular expressions? Right? As I said, they are a really useful tool in programming. Great, but why are you talking about? You should ask me, why am I talking about it in the context of finite automata and a model of computation? Two reasons. One, they're very useful in practice, and the other reason will come up in a bit. But first, just to give a hint of how useful, wait, hold on. Actually, let me just say. So given this, now the question is, if I give you a string X and a regular expression pattern R, how can I check if X matches R? Is this something that I can compute? Given a regular expression R, can I compute the corresponding function FR? If I want to, let's say even forgetting if I want to write a Python program, how does Python, Java, they have like really extensive libraries for matching strings to regular expressions. Perl is entirely just made out of regular expressions. Like, all the computation is crazily just regular expressions. How do they do this matching in there? They use a lot of sophisticated stuff, but at the core is this beautiful, is this theorem, which is very old. Okay, and this theorem is due to Clean from Clean Star in 1956. So long before people were doing implementing regular expressions in computers, what did Clean show? Clean showed that for any regular expression RE, there exists a DFA D such that FR of X equals D of X for all X. For any regular expression, there is a DFA which is essentially equivalent to matching with that regular expression. I can give you a very complicated looking regular expression, but whether, and then ask you, okay, does X match R? I can check this by first building a DFA and then just running X through the DFA. Okay, and not only that, he also showed the converse, that for any DFA D, there exists a RegEx R such that okay. So what Clean did in 1956 is really amazing. He showed that DFAs are equivalent to regular expressions. So from when we look at it the first time, matching a string to a regular expression seems very complicated, right? I have to look for, we have all these star operations. How am I going to do that? That seems crazy complicated. How can I do it? Clean provides an answer. He said, well, there is a DFA corresponding to your regular expression. You first convert your regular expression into a DFA, and then you run your input string X through this DFA. if you get a accept at the end, you say the string matches the regular expression and 0 other ones. Is the statement clear? It's a kind of surprising result to me and very powerful. Any questions about the statement? And how? Yeah, so it seems very common. I mean, so one direction we will see in the next lecture. So the direction of converting any regular expression to a DFA is somewhat easier and you can do it hands-on. The other direction is very complicated. I'm not very complicated. You can do it if I had like 2 lectures, but I think, it's a bit more involved. Okay. Yeah, so you can do it with an NFA. In fact, I'm going to get to that just a second. So here comes, is this related to the formation of KMPs? Not really. You can use this conversion that Clean gave, but it won't be as efficient as KMP's conversion. So KMP also kind of uses the same idea, right? Given a pattern, the pattern P, the string that we are exactly looking for, we are building a DFA, right? And here also we are doing something similar at a conceptual level. We are converting a regular expression to a DFA and then matching. The advantage in KMP is that the conversion to the DFA is more clever and is a bit more direct, and it's much smaller. The DFA you end up with has a much smaller size, whereas here you might end up with a much bigger DFA. In fact, you end up with an NFA. Okay, so let me, we will see, so let's say this is A and this is B. So we'll see proof of A in next lecture. Okay. But let me say something very cool about this theorem, right? If you think about it, there is this tool called grep. How many of you have used grep before? Come on, some of you must have. Right? Do you know what grep stands for? Right. So grep stands for generalized regular expression processing. Okay. And this was implemented by Ken Thompson, in 1973. Yeah, it was, one of the first things. Ken Thompson, of course, is a very important figure in computing. He won the Turing Award for this and many other contributions. But how did he do grep? How did grep work? It uses Clean's theorem. Okay, so the approach that he had was, I'm going to simplify it, oversimplify it. But the way grep works, really, without some optimizations on top to make it industrial strength, is you're given as input a pattern X and a regular expression R. You can call this grep 0.0, like a simplified version, and then the actual thing is much more like sophisticated work. Not much more, actually. It's just more robust version of this. So you convert R to a NFA. Okay, and then you simulate NFA on X. Okay, so grep has two steps. Given any regular expression, we'll use this step A that we are going to sketch in the next lecture, at the beginning of the next lecture, to build an NFA. And then once I have the NFA, there's a way to simulate an NFA without too much blow up in space. And that's it. Okay. And to this date, pretty much this is the fastest way to do grep search, to match a string to a regular expression. Okay. And if X has length n, R has m characters, grep runs in O of n times m time. Okay, grep is really fast, at least for what it is doing. If your string has 1 million things and your regular expression is very succinct, it's only 10 characters or something. Remember, when you think of regular expression as characters, you can't just do, you're matching maybe unbounded length strings too, right? If it says 0, 1 star, it's all possible strings. So grep runs in only O of n times m time. Okay. And in fact, the way you do this is you build an NFA which has only m plus 1 states. Again, this is a little bit analogous, or like O of m states. This is a little bit analogous to the KMP algorithm. And then you simulate NFA. To simulate NFA, it's not linear time. You have to increase the time, but still it's amazingly fast, given how complicated it could have been. Right? So punchline can match regular expressions as fast as naive string matching. Yeah, so there's a question where how come it's not n times m here, not n plus m like in KMP? So the reason is that in grep, you end up with a NFA and not a DFA. And to simulate an NFA, it's more complicated. I can't just simulate an NFA in linear time. I have to incur a loss. Okay. So then why doesn't grep also use DFAs to make it n plus m? Unfortunately, we don't know how to do it for general regular expressions. Like the KMP algorithm, as I said, it's very clever. The way it comes up with the DFA is very subtle, like, it is ingenious. It's not clear how you would do it for much more general patterns. And I don't think even it's possible for all kinds of patterns. Okay. Does this make sense? But still, this abstraction of NFAs and DFAs are baked into regular expression matching, which is a very important practical tool. Okay. This is kind of the best kind of theoretical research. You build an abstract model for completely different reasons, but it's influential in day-to-day practice of algorithms too. All right. And when we come back in next lecture, what we're going to do is look at the proof of this, why any regular expression can be converted into an NFA. We can do it into an NFA without too much trouble. Doing it into DFA is again by our mega theorem that every NFA is a DFA. Okay. Any questions about that? And it's also, I still find it very surprising that you can match all kinds of complicated patterns, right? Imagine think of the fragile X syndrome. Right? So you are matching X, which is a genomic sequence, and the pattern is what is it? It's going to be CGG, GCG, CGG slash. Okay, so that's it. So that's how you're matching. And the genome sequence is billion characters, but then the pattern you're matching is very small, but you can find it in much faster time. Okay, so we'll take up the discussion from here in the next lecture in class on Monday in Moore 100. See you all then.